The sun rises and sets, the planets come and go, but the stars are forever. Unlike nearby objects, the stars of the night sky remain in the same position, and like geographical coordinates, we have a way to locate things based on their coordinates in the night sky. So what is it? Firstly, stars do move, but on timescales beyond our perception. In the same fashion as continental drift, I can tell you the pyramids are at this latitude and this longitude today, but in a couple million years they could be somewhere entirely different. Same with stars. They die, they drift, but for the most part they are suspended in the sky in their position. In the night sky, we basically use the same latitude and longitude, but we call them right ascension and declination. How geography can provide coordinates based on the rotation of the Earth and the geographic poles, we can do the same as an imaginary sphere that encloses the Earth, similar to how a video game might have a world box. We have the two celestial poles which don't move in the night sky, so from anywhere you would watch the Earth spin and the stars slowly move around these poles. The north is indicated by a surprisingly accurate and bright star called Polaris. Watching the night sky long enough, the stars will seem to rotate around this star, and from the North Pole it would be directly overhead. Declination is an indicator of how high or low the star is from this pole, and the opposite pole on the other end of the celestial sphere. The South Pole unfortunately doesn't really have a nice bright star near the pole, but it exists, and watching the South Celestial Pole, you would see stars move in the same fashion. They would sort of pivot around this spot in the sky. We could draw a celestial equator with this, and what we have is essentially a big spherical map that is like a bigger Earth flipped inside out, enclosing our planet, with these three cardinals, the two poles and the equator. Right ascension is how far left or right around this equator the item is. In exactly the same way, we can figure out the geographic coordinates of a landmark, we can figure out the celestial coordinates of a star using its right ascension and declination. But we don't have a prime meridian, or a Greenwich, or 0 degrees in right ascension, so where do we start? Well, when the system was first invented, 0 was defined as the position the sun was in the sky during the spring or vernal equinox, the day between the solstices in the springtime. But the sun moves through the sky. That isn't the sun moving as much as the Earth rotating away from the sun, so the sun remains near the same stars for the equinox. This was originally placed in the constellation Aries, hence the zodiac placing this sign at the start of spring. However, like the nebulousness, pun intended, of me saying the position of the sun at the equinox, this was subject to variability, and the true position of the equinox has actually moved significantly out of the constellation entirely, but the 0 right ascension position remains exactly the same, moving clockwise around the celestial sphere to combine with its declination toward either pole, marking each location on this sphere inside out with a unique number. Now, those with keen eyes might have noticed I stopped calling it 0 degrees right ascension and only called it 0 right ascension. While declination is measured in degrees, 0 to 90 based on where I would see it in the sky from the pole, right ascension is in fact measured in hours, minutes and seconds. The entire 360 degrees around is divided up into the 24 hours of the day, and even though a day isn't actually 24 full hours, it cares about the Earth's rotation. The Earth rotates once per day through an entire 24-hour right ascension value. So a right ascension hour is actually slightly shorter than a human hour and measures distance across the sky more than time. Minutes and seconds behave just like fine tuners for the location around this 360-degree globe. There was an asterisk on Polaris being the pole star. It wasn't always, and won't always be. It's just convenient that it is now, but during ancient Egypt, it was a star slightly over here, called Thuban. Now, calling the star Polaris and it not being the pole star is a bit of a practical joke on future generations, but it happens for good reason. The Earth doesn't rotate perfectly parallel to its orbit around the Sun. The solar system is mostly disc-like, but the Earth doesn't rotate perfectly face toward or away from the Sun. It moves around a bit, like how a spinning top can have its primary spin, being the day cycle, and then have a slight wobble, being this other cycle. This is not the seasons, by the way. This is known as precession. This slight wobble orbits around the North Ecliptic Pole, which happens to be almost directly over the Cat's Eye Nebula, and it does this every 26,000 years or so. However, for all intents and purposes, every star, Every object in the sky can have a right ascension and declination, and I can tell you exactly where I would find it, regardless of where I was standing, regardless of where I was looking, allowing us to standardize astronomy.